Welcome back. I hope you all had a great Christmas break. I know you've probably been suffering withdrawal symptoms from a lack of calculus, so here's your opportunity to get started again. We are ready to talk about the most important topic of optimization. This has many, many, many real-world uses. In fact, the entire section is going to be fun, exciting application problems. You should by now have in front of you a piece of paper labeled example optimization problems. You should also then have one called optimization handout. The handout is your homework. Anytime refers to a handout. The examples are the ones I'm going to do in class. You also have a paper that's sort of a help sheet with these. As with all word problems, the trick to getting these to work is to get them set up right in the first place. So that sheet of paper you've been given is for you to use to double check if you've got your problem set up right after you have tried to do it yourself multiple times. You will discover, however, though, that I wrote that sheet long enough ago that I have rearranged some of the problems so they're not necessarily on the same day they used to be on. You might have to go scrambling a little through there looking for the problems you want because I have rearranged it. But you should be able to tackle that challenge. The whole reason we call this optimization is we are trying to find the best way to do something. In every case, each problem is going to ask you to maximize or minimize something to give the best possible result. Since we just spent a great deal of time before Christmas learning how to find absolute maximums and minimums, that is the process you will be using to solve each one of these problems. Now, as you can see, I already have a list of steps on the board for what we'll be doing. And I'll try to talk you through these. You kind of have to do a couple of these problems before you really get the hang of it and know what it is you're trying to accomplish here. So you have to bear with me as we try our first one. I'm on example optimization problem number 1. In this one, we're talking about a farmer. Today's problems are what I think of as the area problems. This farmer wishes to enclose a rectangular field with a fence and then divide the enclosed area into 3 sections by putting 2 fences down the middle. Perhaps he wants to keep 3 sets of cattle separated. He only has 3,000 feet of fencing on hand and does not want to buy more. What dimensions should he use to form the perimeter so that it encloses the largest possible area? He's out to get maximum area inside his fence, but like all farmers, he doesn't want to go spend more money, so he's only going to use the fence he's got on hand, which is 3,000 feet. So if you notice, the first thing it suggests you do is you draw a picture and label it. Okay, in our case, what do we need to label it with? Well, it says we're looking for dimensions. So we need to, and I'm going to use width and length. I'm going to refer to the long complete width as, or complete length there as a length, and we're going to call the width each of these short sections. Now, the big tip of the day here is we have 2 variables in this problem. If you have 2 variables in the problem, it will take 2 equations to solve it. If you have 3 variables, you need 3 equations. If you have 1 variable, then you'll only need 1 equation to get it done. In this case, when you have to have multiple equations, where in our case we need 2, you will always have 1 equation that is the functions you're trying to be maximized or minimized, and the second formula will be what limits this thing from just going astronomically huge. So in our case, what is it they want us to find the largest or smallest of? Well, it asks for the largest or smallest area. So our function is going to be a function for area. And at the moment, how do you calculate area of a rectangle? And of course, you're all saying, yep, length times width. Okay. The second equation you're going to need has to be something that limits you from preventing this from being an infinite area. So what is it that limits this farmer from just having the largest field known to man? Well, it's the fact that he's only got 3,000 feet of fence. So my question to you is, what parts of this are going to be fenced? Well, everything we have labeled. So if I sum up all the things, all the parts of this fence, you'll discover that you have 2 lengths plus 4 widths, and that has to equal his 3,000 feet of fence. Okay, before we can optimize this or find the absolute maximum or minimum, we have to have our function in one variable, because we know we're going to need to take the derivative of this and find the critical point. So I need to get the area formula turned into all one variable. It either needs to all be L's or all be W's. It doesn't matter which one you use. I personally decide, I come over to the second equation we wrote and I look at it and go, which one of those variables would be easiest to solve for? Would it be easier to solve for the L in the 2L or the W? Well, I look at it as I would solve for L because it's really easy to divide everything by 2 and I won't get any fractions. So I'm going to opt to solve this equation over here for L, which means I am subtracting the 4W to the other side and then dividing the entire equation by 2, which will take L down to 1,500 minus 2W, which isn't a bad expression. You then take that L and come over here and replace the L in your function with it. So I'm going to have 1,500 minus 2W times W. And of course I want to distribute that because I really don't want to do a product rule. And so I'm going to get 1,500W minus 2W squared. Now that you have this in a nice simplified form, this is what we will think of as our original equation, the original function we started with. That's what we're trying to maximize or minimize. So how do we find a maximum or minimum? Well, we'll have to find the critical point. Now you'll notice if you're reading my set of instructions, it tells you on step 4 to change the function to one variable, which we did. And in step 5, it then tells you to find the interval for that variable. Okay. If you recall, when we did absolute maximums and minimums, you got intervals like 0 to infinity or 1 to 5. And it was the type of interval that influenced what method you used to figure out if it was an absolute maximum or minimum. So in this case, I have to actually figure out, though, from common sense and the information given to me, what interval is possible in this situation. So the key thing, though, is it depends on which variable you used in your function. In our case, we changed our area function into all W's. So we are writing a formula, or excuse me, an interval for what W can be. So here comes the common sense part. What's the smallest W can be? How small can that width get? Well, we know it can't be negative. Can the width be 0? Well, it really can't be 0 because if we have 0 width, we'd have 0 area. So, but it could be a width of 0.1. So it could be a very, very small number, very close to 0, but it can't be 0. So therefore, we're going to write our interval as 0 with a parenthesis. Okay. The low side is always the easy side to get. It's the high side of the interval that causes people the most trouble. I have to figure out what's the largest width I could have. I can't have an infinite width because I've only got 3,000 feet of fence here. Now, can width just be 3,000? Well, no, because I've got 4 of them. That causes me a problem. The easiest way I can tell you how to find the high side is to go back to this second equation we wrote, the 2L plus 4W equals 3,000. That equation is what limits our size. We want to figure out how big W can get. So if W is going to get big, what has to happen to L? Well, L has to get as small as possible. So I'm going to let L come up to that equation. I'm going to say if I pretend to let L be 0, that's gone, and I'm left with 4W equals 3,000. Solve for W. 3,000 divided by 4 is going to be 750. So that's the largest my W can get. It can't equal 750 because that would actually give me an area, once again, of 0. So it's parentheses from 0 to 750. That, for a lot of people, is the hardest part, coming up with the interval. Okay, now, the rest of it's just do the calculus. Step 6 says we've got to find the critical point. So come back over here to your function and do the derivative. That's going to give us 1,500 minus 4W, which is going to be no big deal to solve. 1,500 equals 4W, which means W equals 375. Now, does that mean that's the correct answer? We don't know for sure that that's what's actually going to maximize the area until we prove it. Okay. In a lot of cases, the critical point is going to turn out to be your answer, but not in all the cases. So you cannot trust it. Oh, I'm done right here. If you do not go through the process of setting up an interval and testing to make sure that our critical point really does give us maximum area, you're going to lose 5 points on every problem come quiz or test time. That's a lot to lose. So now, it's a matter of remembering, how did I test for an absolute maximum? Well, since this thing has parentheses on it, you'll recall we had to do limits. In our case, our variable is W, so I'm doing the limit as W approaches 0. And I'm going back to that function I starred as my original function. And I'm going, okay, if I put 0 in, let my limit go to 0, yeah, I'm going to get an area of 0. And since the other end of the interval is also a parenthesis, I have to do a limit on it. And you'll find out that if you, once again, first rule of limits is sub the number in. If you sub the number in, you'll get 0 on that one too. Okay, now, how do I prove that my critical point is going to give me maximum area? Well, the point then, if you recall, you had to prove that your critical points in this case, came out higher than your limit. So we got to prove our critical point comes out higher than 0. So technically, we t-tabled, we put 375 in, and we found out the y-coordinate of our function. Well, since we're not really graphing anymore, that's not how we write it now. Instead, we're just going to say, we're going to find the area at 375, since that's our critical point. You're going to sub 375 into that equation, and you are going to find out that you get 281,250. Okay, is that higher than your limits? Well, sure it is. So since it is, that means our critical point must be our optimum solution. And we have now done step 7. However, step 8 is a step that often gets left out. Have we actually answered the question? Did we find out what they wanted us to figure out? So the question was, what dimensions should his perimeter be? Okay, well, we have now figured out the width should be 375. How do I find out what the length should be? Well, usually the best place is to come back up here to where you have the equation where you solved for L in the first place. This L equals 1,500 minus 2W. Well, let's find length. So I'm going to put 375 in there. 2 times 375. And you're going to discover we're going to come up with a length of 750. So therefore, the perimeter of our particular rectangle, it should have a length of 750 feet by a width of 375 feet. And you have solved your first optimization problem. Okay, I'm going to stop it right now because I'm about to run over the 15-minute mark. I'll be back in a moment with part 2.